Graham would be here to talk to you and introduce me, and also to welcome you. So I'll welcome you anyway to here today. How many people have been to Daresbury before? Have you all been here before? No, some haven't. How many of you have actually attended, visited an accelerator, a real accelerator, been around an accelerator? Most of you. How many of you actually had any previous training in accelerator, been into a course or part of a course as an undergraduate, for example? No, not a majority. Okay, good. So my name is Mike Poole, and I used to be the director of Aztec, which is the Daresbury-based accelerator group, accelerator department, if you like. And the idea is that I give you a sort of a warm-up talk, or two talks, as it turns out. Some of the talks you're going to have over the next few weeks will be quite heavy, quite academic, quite rigorous, quite demanding, quite mathematical. It's part of our belief that everybody should have a grounding in accelerator science and accelerator physics in particular. Even if you go on to do more specialized things later in your careers, it's better if now you absorb all the broad breadth of accelerator science and technology, both RF and magnets and vacuum and all the other things that go into making an accelerator. We just think it's important, so we'd like you to sort of try and bear that in mind. It's good to be broad at the start. You can specialize as time goes on. Even within your PhD, you can specialize as time goes on. Some of you may already have got a topic, some of you may not. Perhaps this will help you to decide what to work on. So what I'm going to do is very much in the first talk to tell you something about the history of accelerators. And in the second talk, later on this morning, I'll give some examples of some modern day challenges at the three frontiers of accelerator science and technology. That gives you the sort of themes, if you like. So I'm going to assume, bear with me if you've got some knowledge of accelerators already, I'm going to assume more or less no knowledge at all at the start. So why did we, excuse me a minute, I'm trying to find my pointer. There we go. Why were accelerators developed? Well, they were developed, of course, for what would nowadays be called particle physics, but wasn't in those days. And these early 100 years ago, great times of great discovery, the only way you could study the scattering within materials was with radioactive compounds. And so radium, it was very important because of these. I'm sure you've all done something about alpha, beta, gamma particles. And they were a few MeV. This is numbers worth bearing in mind. So there were a range of particles available in the laboratory, from a few hundred keV up to a few MeV. But more or less, that was about the most energetic particle you could get. And bear in mind, these sometimes were very, very low intensity by modern standards. You got a block of material, it was dangerous stuff anyway, although people didn't realize at the time quite how dangerous it was. Yeah, I'm sure you all know the story of Madame Curie and radium and the dangers to the people's health. But of course, in 1909 was this great seminal experiment at Manchester. Who's from Manchester here? So you've got a great history at the start of particle physics. I mean, this is where Rutherford did his alpha backscattering, where actually Geiger and Marsden did the actual experiment, but Rutherford sort of looked after it. Can you make sure you sign in, please? We've only just started.
Yeah, sorry.
And in this period here, from when this backscattering experiment was done, remember the experiment was the one that proved that an atom had a solid, small, dense core, and most of it was empty space, because of the way that the scattering was occasionally 180 degrees, but most of the time things went straight through. So it was a really important experiment, but obviously it begged the question of what more work could be done. And Rutherford was very much in the fore about 1920, well, not about exactly in 1927. There was a meeting, I think, of the Royal Society, and a paper was presented to the Royal Society by Rutherford, who demanded the development of artificial sources, particle accelerators. So that, if you like, was the start of it. And Cockroft and Walton were the people who were engaged on this project, because Rutherford moved to the Cavendish in Cambridge in that period. He was now at the Cavendish in this period. And so Cockroft and Walton started these high voltage experiments to try to create an energetic million-volt particle, because the theory at the time had proven that you needed about a million volts, an MeV. And with a million volts, you could get tunnel into the center. Well, I was going through my words here. You could scatter off the center of the nucleus. If you get over the barrier, the potential barrier, you needed a million volts. As it turned out, you did not need a million volts. the irony of this experiment is that people had worked very hard to get 1,000,000 volts, but the theory was actually wrong in the sense that it ignored tunneling. Now, some of you may have studied tunneling, but tunneling meant you didn't have to go over the potential where you could get through it. And you actually only needed a few hundred kilovolts. And if they tried the experiment as a few hundred kilovolts, they would have succeeded. But they waited until they had the energy that they thought they needed, which is an interesting little piece of history. But they split lithium with alpha particles, with protons rather, and they did it by brute force. And the important, I'll just get rid of that. Where that's come. They split lithium, and it's important. Let me show you an experiment. So there's Roland Rutherford. There's John Cockroft as a young man, youngish. He looks old, doesn't he? But he's actually only about 28 or 30 years old at the time. But my word, he looks old. And Rutherford, of course, was about 70, I think. And this is Walton, who after the experiments disappeared back to Ireland and spent most of his life, academic life, in Ireland, whereas Cockroft spent a lot of time in England, became a very famous man, and ran the Atomic Energy Authority, for example, in England, was very much the leading figure in particle accelerators for about 30, 40 years. The project involved trying to get a discharge tube with, as we said originally, about 1,000,000 volts, but in fact they in the end went for 400 kilovolts. It's about the most they could get. They had big problems getting high voltage, and there's lots of problems working with high voltage. It's interesting, as you'll see, that 400 kilovolts, which is the voltage they were trying to achieve, even today is quite difficult and quite demanding to achieve voltages like that. In this sort of apparatus, where you had glass insulators, if you like, protons were discharged at the top, were accelerated to the bottom. They then detected from the lithium target the alpha particles coming out. How did they detect them? They sat in a box and looked at this insulator. So the actual experimenter sat in a box in the room at the bottom here and crouched himself down in the box with black things over him like an old photographic recording laboratory, and looked for twinkles on the screen. It's amazing when you think of they won a Nobel Prize that way. But there we are. One point I wanted to make about this work, even in the 1930s, even at this stage, the collaboration with industry was vital. And this was the start, we're talking about the 1920s really, the start of the electricity generating era around the world. This is when people started installing big sets of power transformers. This is when the grid was starting to be put together in the United Kingdom and other countries, although we're well ahead in the UK of most countries. And so there was a deep collaboration, and John Cockroft had a lot of collaborators in industry, back up here in Manchester actually, and they were able to borrow kit. We were able to take loan of things from industry, or even were given certain gifts by industry that were surplus to requirements. And that is worth remembering because it's quite vitally important that we keep the collaborations with industry going. The so-called Cockroft Walton set, which was the thing that created the high voltage, was in effect a ladder system. I won't go into the details of this circuit, but in fact you charge up and discharge capacitors and gradually build up the voltage on a ladder so you get to high voltage. And this is actually called the Cockroft Walton set, and you'll see it referenced and cited all over the place as a Cockroft Walton generator. You can even, if you put Cockroft Walton in on your web search, you'll get loads of results for the Cockroft Walton. This is actually naughty, if I can use that phrase. Because actually this circuit and this voltage system was invented by this man Greinicher 10 years earlier. They just copied somebody else's circuit. It should not be called a Cockroft Walton set, to be frank. Even though they were the Nobel laureates, they've not got a right to this circuit. It belongs to somebody else. Anyway, leave that one aside. This Cockroft Walton generator was in use as an active circuit in accelerators until 2005 in the UK, in the Rutherford Appleton laboratory, in the ISIS neutron source. They used this circuit still, the Cockroft Walton set, for their gun, for their early voltage, for their first set of accelerators. And they only got rid of it in 2005, which is absolutely incredible when you think it was first used in, 1929, 1930, and it was still being in use as a circuit. If you go and look outside, if those of you who haven't noticed, when you come in through the door, you'll see the remnants of the ISIS Cockroft Walton set. We decided rather than throw it all away, it would be useful to have it as a memorial, and it's in our atrium now outside. Have a look when you go outside if you haven't noticed it already. So what were the early challenges for accelerator people? High voltage breakdown clearly was a problem. We were pushing this thing to hundreds of kilovolts without really any real understanding of breakdown, no theoretical understanding at all. Practical, pragmatic solutions were adopted. People realized, for example, that sharp edges had to be avoided. You had to round off everything. You had to skirt. Now everybody knows now there's a reason for that, which is the concentration of field lines. But they didn't really understand that in the 1920s and 30s for sure. You know, you will use nowadays in your practical work vacuum systems, which seems effortless. But at the time, there was a lot of problem with seals. What did you use as sealing? People use grease. You know, as if you can imagine trying to keep a vacuum through a grease seal. People use rubber systems, which rotted or even suffered radiation damage. There are all sorts of primitive materials in use as sealing compounds. The currents in use were very low. Getting to higher current was very difficult. Diagnostics, you know, perhaps it's true of every field of science, but for particle accelerators, remember when you're doing experimental work in the future, diagnostics, diagnostics, diagnostics. If you haven't got the diagnostics, you've got big problems. Get more diagnostics than you need. Fight for diagnostics. If you're in a project team and people are saying, you don't need that, you don't need that, fight them. Diagnostics is vital in everything you do. The small industrial base, although that did start to grow, and the scale. I mean, all of the physics and chemistry of the time was done on benches in the 1920s. Now we're moving into the era of what we now call big science, where you build special buildings and special project areas, and this was foreign to the culture at the time, and did cause limitations. So I want to say just a few words about electrostatic accelerator development, because I want to relate most of what I say for the rest of this talk, the first talk, to what happened here at Daresbury and how Daresbury has got involved in these various things and in this history within the world scene. So electrostatic accelerator development, that means building accelerators with higher and higher voltages to do this simple task of injecting particles in at one end, accelerating right down the line of the voltage, which might be hundreds of kilovolts, it might be more, we'll see. In 1927, already people were building megavolt transformers in the US, not in the UK. And this guy, Van de Graaff, you'll have heard of Van de Graaff accelerator perhaps. This is an accelerator where you charge up the voltage terminal on a belt and you inject charge at the earth level, and you, in effect, you do work on the pulley belt system, and then you take the charge off at the top into the electrode. There are usually quite small versions of this, even in schools, as teaching apparatus. The first big experiment in UK was done in 1961 at Liverpool, a collaboration with Manchester, you might be interested to know, at that time, even all those years ago. And they built a 6 MeV machine in Liverpool. And in 1972, they started to consider a world-class machine. In fact, a 20 or 30 megavolt machine would be twice as big as the biggest machine anywhere in the world. So the highest voltage anywhere in the world at that time was about 14 or 15 MeV, and still is, by the way. These things are available still, Van de Graaff type machines. And in 1974, they decided to build something, and they built what you see outside now, the tower. So the tower that you've seen as you come down the hill, I hope you've all noticed it. You can go in it still, you can go to the top still. And the NSF, Nuclear Structure Facility, was commissioned in 1983 and ran for nearly 10 years before it was closed. So that's what the tower looks like. Just for your interest, just quickly, at the top is where the ion sources are. A whole range of ions, right up to uranium, have been accelerated in this machine. The terminal is actually not at the top or bottom, it's in the middle of the tower. So this tower is about 60, 70 meters, I forget the exact dimensions, it's about 200 feet high. And the terminal is in the middle, and it uses a trick. And the trick is that you put the positive voltage on the terminal, and you have a negative ion species with surplus electrons injected on them, extra electrons. They then accelerate down to the area in the middle, and they go through a stripper foil, and the electrons are stripped off. So you convert from a negative to a positively charged particle. So the positively charged particle emerges and is then accelerated again by being pushed away by the positive terminal. So you get your acceleration twice over, which is a nice little trick. It's called a tandem accelerator. And so down at the bottom is the area where the experiments are done, and that's in plan view. There are a number of areas that are no longer like this. It's been taken over, as you'll see later on this morning. That's what it looks like. Ion source, In the middle here is inside a huge pressure vessel full of sulfur hexafluoride gas, which allows the breakdown voltage to be much higher than if you used atmospheric air. This is actually, in principle, was a health hazard because there's several tons of sulfur hexafluoride gas in a tube in the centre here, and if it leaked, it would actually roll down the hill down to the laboratory at the bottom where everybody is, and in principle have a hazard from suffocation. It's not toxic, but it could suffocate you because it could displace all the oxygen in the ground level. So there were a lot of concerns about that at one time. Anyway, it's not there any longer. There's no health sulfur hexafluoride. But this is the sort of phenomenon you get when you try to go to millions of volts. You get lightning breakdown strikes, even though this is beautifully constructed. You see all these smooth surfaces, all these earth surfaces here are smoothed out and down to micron smoothness to avoid these hot spots, which could cause discharges. But still, a tiny bit of dust, or even perhaps even a foreign molecule could stimulate the dust. Anyway, so it's not a great idea doing this electrostatic stuff. If 15 million volts was the world record in the 1960s and 70s, you can see how little progress you make on the few MeV that radioactive compounds could produce 50 years earlier, 60, 70 years earlier. So then we need to go and look at other concepts. And this is the resonant accelerator concept. So what you've got is a series of accelerating gaps. So this is a tube split up, and the acceleration occurs in the gap. So the tubes alternate in voltage, so you've got a plus on one, you've got a minus on the other, so that they actually accelerate. So if you've got a positive charge coming in here, it wants to be accelerated towards a negative charge. So each time you get to the gap, you need the negative charge to be there, but the voltage is going up and down. So now you get the idea that you have to phase this. The particle has to arrive at exactly the right time when the voltage is in the right direction. If it arrives half a cycle too early, it'll get decelerated. It'll meet the wrong field. Is everybody clear about that? So this AC voltage was put on these things, and you've got the benefit then of multiple acceleration of many gaps, and you could have in principle as long as you like if you could afford it, and just keep adding up voltage on it as the particle goes along. But this produces the idea that because only certain arrival times are accelerated and certain are not, you get gaps in the beam. So now the beam starts to get bunched. You get holes in the beam. It gets bunched at the frequency at which you are varying the voltage. So now you get this concept, a very important concept. Nearly all the accelerator beams you'll meet in your lifetime will be bunched. It's something to do with some accelerator, because nearly all accelerating systems are nowadays radio frequency driven. So the bunching is on a radio frequency timescale, which might be nanoseconds or even faster. But in this era, we're not, of course. In the era we're talking about when Linux were first invented by this man, Dorrough, who's, if you like, the father of accelerators. He invented the first Linac. There's the Dorrough Linac. In 1928, he operated it with an iron source. You'll notice here that these tubes get longer. Why is that? They're not all the same dimension. The electron gets accelerated, and because at this point in time, or the particle, it probably wasn't an electron, it's probably a proton at this time, or an ion. In this era, we're talking about ions which are relatively low energy. So there's still the velocity increases when you accelerate them. They're not relativistic. And so as the velocity gets greater, they will go faster. So you need to stretch the gaps a while, otherwise they'll arrive too early if you keep the gaps the same dimension. So that was the first example of a way that you made sure that you synchronized and bunched the electrons. And the Alvarez structure, which came 20 years later after the war, changed this system from a series of tubes, which nobody would use nowadays, to a series of electrodes buried inside an electromagnetic chamber, if you like, an electromagnetic field, which you could do very efficiently. So that you could fill this tube here with radio frequency field. And here is an example of one of the very early such Linacs. This was taken at CERN, built in 1958. And this accelerator, you can just about see these little grid things here. They're the equivalent. You can see them getting longer as you go along. Well, maybe you can't see it very easily, but I can assure you they do get longer. So what are the challenges of building these Linacs? Well, developing power sources, and what is the energy limit you can put into these things? Electrons, the velocity gets so high, so quickly, that you need very high frequency. And the technology just wasn't there in the early days when these were first developed 50, 60 years ago. Beam dynamics are not as simple as they look. the field across those little gaps is not parallel. It tends to be curved field with all sorts of non-linearities into it, which mess up the beam. So you have to worry about the fields at the gaps. You needed correction fields. Permanent magnet solutions were introduced, and there are scale issues. Even then, even now, you only get a few MeV per meter. So your LINAC becomes very, very long indeed, even though it's nicely synchronized. So what's the answer to that? The answer to that was invented by Lawrence in California at Berkeley. It used to be called the Lawrence Berkeley Laboratory. I don't know whether they still use that phrase. So what do? You take these tubes and you bend them round. So now instead of being in a straight line, you only need 2 tubes like this, and you go through the same tube over and over and over again, circulating by sitting these things in a magnetic field. And the interesting thing is about this particular arrangement is if you put very, very simple Lorentz equation in, very simple maths, QVB, the force from the field, mv squared over r, back to school days, and you rewrite that in this way, you find 2 things. First of all, the radius of the beam scales exactly with the momentum, mv. Note it's momentum, not energy and not velocity. So it's got a mass term in it there. The field is assumed for the moment to be constant, and the charge of the particle is constant, so the radius comes out in a spiral, linearly proportional to the energy. As the energy increases, the radius increases. What happens to the time for circulation, the phasing, the synchronizing time? Well, marvelously, there's no energy term in there. There's a mass term, but the V is gone. So the time for circulate once in the orbit is only proportional to the field, which is constant, and the mass, which at low energy is assumed to be constant. So it's constant. So the thing self-corrects. It goes out to a bigger orbit, which allows it exactly the same time of travel, which synchronizes with the radio frequency system. So it sort of helps you. It's a built-in synchronized system called a cyclotron, which is nice news. But don't forget the mass term in there. Once the mass starts to vary, you've got other issues. And so there are 2 issues with cyclotrons. First of all, it's nice that the thing spirals out, but of course that means the magnet has to be absolutely huge, because the magnet has to be a continuous field right from the center with a small radius right out to the maximum radius you want to have, which is the maximum energy. So you can imagine these things getting as big as, say, this area here of all these chairs. There have been magnets built that big. You can imagine what that costs and what it weighs and how you would deal with a magnet. It's just impractical, became impractical. So, and also the desynchronization problem of the mass starting to vary, it was another problem. So what is the solution? Well, the solution is quite straightforward. What you do is you raise the magnetic field in proportion to the increasing energy of the particle, and this produces a fixed radius, not a spiral radius. And then you have something called a synchrotron. Now, I just want to say something else about a synchrotron, because if you're going to have a fixed radius, do you get the synchronization? Well, you do, because you get something called phase synchronism, which is why the synchrotron is called a synchrotron. The phase synchronism, which leads to bunching again. If you just look at this little diagram here and take a test particle A, which is what we'll call the synchronous particle, the reference particle. This is the amount of voltage kick you want to have each time. And if you are too high in, if you arrive early, having done a circuit by an energy which is not quite the right reference energy, then you arrive early, you get a kick, and the kick pushes you out onto a larger orbit. It can actually work either way, but it actually compensates you by going on a different orbit. So the next turn you'll have a different time, and the time will correct you back towards the reference time automatically. So the particles have sort of harmonic oscillations about this reference point. Too much energy, they go out to a bigger orbit, they take longer to get round, therefore they get slightly less different kick. So I'm sorry if that's not quite clear. Do people understand that? Perhaps I haven't explained that very well. I think it is pretty obvious when you think about it. The time you take to go round depends on the energy. Therefore, a delta E can produce a delta T, which corrects you back to, and the delta E puts you back onto the reference orbit. And so you can build a synchrotron, which is an annular device. And these are a combination of bending magnets and focusing lenses. You can imagine you do need some focusing. I haven't talked about focusing yet, but you can imagine that it's not easy if you're going to go many, many turns around these machines to keep the beam together. So you need some sort of focusing system, which I'll talk about in a minute. They're all in a vacuum tube, and somewhere you have an accelerating cavity. You can put it anywhere you like, in principle. Sounds like you can put it anywhere, it just gives a kick. Maybe you have more than one. Many accelerators have these in many places around the ring. where you can fit them in. And the bending and focusing in the early days were very often combined together into one magnet, one type of device for convenience. And here is an example of something called a quadrupole. How many people have seen a quadrupole? How many people realise the consequence of a quadrupole is that it focuses in one plane and defocuses in the other? Do you realise this is the problem with a quadrupole? A magnetic quadrupole, you've only got to do a little test here with north and south poles, and you can see that in one plane the force is towards the axis, and the orthogonal plane it's away. You can't defeat that. It's Maxwell's laws, basically. So what you have to do is you have to have what we'll call a focusing quadrupole, then you have to have another type of quadrupole where you rotate it through 90 degrees. That you call that a defocusing quadrupole. In other words, you change the north to a south and the south to a north all the way around. And in combination, these quadrupoles, where you can see a real quadrupole here with 4 poles and exciting coils around it. So in practice, in practice, these quadrupoles here can combine together to produce, as I'll show in a minute, a lattice, which is focusing in both planes simultaneously. That was just an attempt to show you next. That's really not terribly useful, just to show you a cavity which is a single cell. We'll say more about that later. And these are Klystrons, which we use here at Daresbury. I should jump now to some proper particle optics. I think that was a bit too elementary. So when these cyclotrons were first built, Ernest Lawrence pioneered them, made them work. But he realised there were lots of problems with this type of accelerator. First of all, he had to shim the magnets tremendously. That early cyclotron gave the clue that a lot of pragmatic focusing compensation for errors would have to occur. There were many errors around in the system. The errors are not just in the practical magnets that you build. The errors were in the fact that the beam itself is not linear. There are non-linear behaviour which dominates things, which has to be compensated for. However, when you built a synchrotron, you built those magnets in periodic units. And all the accelerators you'll meet in the world, I believe, you'll find are periodic units. In other words, there's a basic unit which is repeated many times around the circumference of the accelerator. And this gives a periodic structure which puts certain conditions onto the system. If we forget coupling, then most of these accelerators, and you'll have some couple motion, I think, later in your lectures, but most of the early analysis of accelerators can be done by assuming that the two planes, vertical and horizontal, are decoupled. And provided they're decoupled, you can analyze the motion in the horizontal plane independently of the motion in the vertical plane, which is very useful. Once you start having coupling, it gets extremely complicated if energy is feeding between the horizontal and the vertical, but we'll assume it isn't for the moment. The solutions can be written down as Hamiltonian solutions because it's a periodic system, but unless you're going to go into theoretical physics, possibly anybody who's a student at Lancaster might, if you're at Lancaster physics, you might be involved in some of these theoretical, but most people nowadays would not bother with Hamiltonian solutions. I shouldn't trivialize it. I shouldn't say don't bother. Hamiltonian solutions are very complex and very difficult for the full practical system. So what people nowadays use, of course, is simulations. And simulation codes you'll find yourself using, all of you, I'm sure, will use simulation codes. But just always remember, rubbish in, rubbish out, rubbish in the code, rubbish out. Who knows what's in a code? I'm very personally very uncomfortable using a computer code if I haven't actually worked out how it works. But you'll be invited to use codes which may be quite difficult for you to work what's inside them. So bear it in mind. The codes. I could even be a real heretic and say, I wonder sometimes about these meteorological climate codes, because I know what it's like with accelerator codes, and you do wonder how many assumptions are built into these codes, and whether even the owners of the codes have absorbed the assumptions they put into the codes, because I know from experience in accelerators that we've sometimes made that mistake. And we should remember always you can make mistakes. What actually happens with these correcting things is you get some sort of, if you like, simple harmonic motion. The particles swing around backwards and forwards as they go around the machine. They swing around quite stably, but they're not zero width. So any given particle will oscillate as it goes around the machine, but it will oscillate stably, provided you arrange for it to do so. And of course and then it will have what's called the tunes, when you go through all this in detail later, in later lectures. You can get resonances if the tunes are the wrong shape, the wrong numbers. And the beam itself is made up of huge numbers of individual particles. So you now need a representation which represents the whole of the beam rather than a single particle. and the whole of the beam is represented usually in phase space, so by an ellipse. The phase space, if you like, is position and angle of any given particle. So any given particle around that machine has a displacement off axis and an angle off axis, off parallel. And if you like, the angle off parallel is actually transverse momentum. So what you're looking at is the errors in the position and the momentum of the beam, which is why it's Hamiltonian. Momentum, position, paired ensemble of particles. The phase space area is called the emittance. You can see it here. So the area of this emittance can be a characteristic of the beam and how much parallelism there is in it. So this is what I was trying to show you earlier on, and I'd forgotten I did it later. So this is an example of a real lattice, where you would have to have a focusing and a defocusing combination, because you have to focus in both planes, horizontal and vertical. So you have to have both types of magnets in there. This just proves the point. The envelope of the beam can be kept stable, even though it's going through divergent as well as focusing lenses. And this is called a photocell, F, a D cell, and the O is for a straight section between them. So you'll come across this as the basic first cell that was ever invented. So these are the periodic units that are repeated many times around the accelerator, as you can see here. And within here, of course, individual particles are doing all sorts of things, but they're remaining within that envelope. No particle goes outside the envelope, so that defines the beam size or its emittance. This is more like what a real lattice would be like nowadays. If you went to a modern lattice, it was all very well having that photo lattice if all the particles were the same energy. But as soon as the particles have a spread of energies within them, you get what might be referred to in optics as chromatic behaviour, same as you would get in optics. In other words, the focusing and defocusing lenses would have different strength for different energy particles, and this causes a problem. And also, if you're bending around a big bend, you would start to get a divergence within the bending magnets themselves, because the bending magnets themselves are fixed field, and if you have the wrong energy, you don't get the correct bend, which you get you around the ring. So this unit was invented here called the double bend achromat, and this is two dipoles in combination. If you put a quadrupole lens in the middle of the correct strength, then the error due to an off energy particle bending itself out can be self-corrected within this unit. So you do get some offset of energy dependent particles within the bend, but outside the bend, everything is still in a straight line, even though there's a range of energies. So this is a basic building unit that will be used when you come across in many accelerators. In fact, nearly all accelerators, circular accelerators. There's an example of a real machine. Now you can see here is one unit, here is a second unit, here is a third unit. So these are in blue and purple, give you what are called the beta functions, which gives you the beam size. So the reason I show you this is to show you that when you are within an accelerator, a ring accelerator, the beam cross section is varying through the lattice, and it's varying in each cell. And you can see there are huge variations between minimum and maximum beam size. I mean, a beam size might go down to a fraction of a millimetre in some places and be tens of millimetres somewhere else, although that's not common. Also, you can see here there are some larger spaces here between these units, and these are where you would put many of the other apparatus. The radio frequency cavities, for example, would have to go in some larger space in between the bends. There might be all sorts of things in there. There might be, you'll see that they're on radiation generating functions as well. So that's an example of that's a real lattice. I think that's actually a diamond lattice, but I'll come back to it later on. How are we doing on time? So I want to say something about errors. That's very important as we start to tell the story of real accelerators. Real accelerators are non-ideal, yes. Misalignments, physical misalignments of components when they're put down and surveyed into position. Misalignments within the field structure of components, the way they're built, must be corrected. Non-linear behaviour must be corrected. The whole area of analysis here, which some of you may choose to work on. This means we have to have correct diagnostics, and we also have to have correctors built into accelerators. So you diagnose an error, you work out what to do about it, and then you apply a correction. So that term in modern accelerators tends to be in a feedback loop, as you can imagine, where you don't do a calculation in the control room. The system does it automatically for you. You sense an error, you do a calculation within the computer, and then you apply the correction. And the error, you never see the error. The error in effect is stamped out before you see it. So feedback theory and all that sort of stuff is built into accelerators as well. There's a big whole field of area of work there. Very complex analysis. which you'll get your fill of, I think, later on. I just wanted to give you one example of nonlinear behaviour, massive nonlinear behaviour. I talked about off-energy particles before, this what we call chromatic. And there is a way of correcting for off-energy particles in the focusing systems of an accelerator. And if you put in a sextupole, a 6-pole device, in other words, as you can see here, then the field variation off axis goes as a square of the field. In other words, the gradient of the machine, if you differentiate once, goes linearly. dV by dx is proportional to x, not x squared anymore, because you go down with the differential. And so now you get across the axis of the magnet, the gradient of the magnet varies linearly with offset. So if you can arrange the orbits to vary across there with dispersion, so the off-energy particles also vary linearly off axis, they can match them to the positive or negative extra focusing increment that comes from this magnet. So it's a way of correcting for dispersion, and it's very popular and most machines want to have it. So they put them in. So let me go back again to phase space. These are phase space plots. So here is position and here is angle. And this is a beautifully symmetric plot when there are no such pairs. This is a pure linear machine. This is what it looks like. Wherever you put a particle, it's stable. So these are the particles which are within what's called a stable aperture. Any of these particles here are stable. They keep going round and round the machine without a problem. If they're not stable, then they remove themselves. If you switch on those chromaticity correcting sextupoles around a typical machine, this thing collapses to this. So suddenly, by putting these sextupole fields into a machine, which are put for an entirely reputable purpose to correct the chromaticity back to nothing, so there's no off-energy effect, you introduce such a big nonlinearity in the orbit dynamics that this thing hardly has any space where it's stable. So all these particles here have gone. They're not stable. Any particle here is gone. It won't keep going around the machine. It gets lost within a few turns. Now you can actually correct this, interesting enough, by having more than one family of sextupoles. In other words, if you put the sextupoles in a certain manner distributed around the machine, there are solutions that can be found that almost restore, depending on how many families and how thoroughly you do it, because this is an added complication. So you've now got sextupoles to correct the chromaticity. Those sextupoles have to have a built-in correct themselves by a distribution system, which depend on the machine setting in a complicated manner. But you can just about overcome this in the end. But it's a really hard work, and that's what an accelerator designer who is doing the basic design of the dynamics of a new accelerator will have to conquer, will have to have a solution for. What about engineering challenges? Well, physicists tend to use this idea of beam stay clear aperture. In other words, when you're designing a machine, you work out the aperture in the machine which needs to be clear and kept clear for perhaps for dynamics, perhaps for other reasons, perhaps for components that need to get that close to the orbit. So when you're building the machine, you have to define the components to have apertures that are that big. The magnets have to be big enough to have these defined apertures that are required in there. And for these, to allow for errors, for example, to allow for injection into the machine, you might have to have some problem where you've got the vacuum chamber. The vacuum chamber has its built-in tolerances. You've got to allow for that. The wall thickness, the alignment, the mass production issues, radiation hardness. How close to the beam can you allow components to go? Because they might get particles scraping off and hitting them and damaging them. So there's a whole area of control engineering and all this. Reliability comes into it as well, of course. So although I guess perhaps all of you in the room are either physicists or perhaps electrical engineers, or think of yourself as such, because I think in accelerator technology circles, physics and engineering are really very much merged nowadays. They're not too purely separated. So that was a sort of a basic introduction to the sort of some of the dynamics challenges of modern accelerators, but looked at historically. I'd like to now sort of the rest of this first talk just say something mainly about this site and how it came to be here and what it's done. And just to start that, let's look at the early history in the UK. I've put the Berkeley machine in from 1939, but I want to show you what's been done in the UK. So cyclotrons, there was some work done around the time of the Second World War. These cyclotrons were the machines on which the experiments were done that worked out the cross sections for the neutron reactions for the atomic bomb. So what actually happened here in 1939, the Liverpool people got this machine working and wanted to build a big machine. But all these guys who worked at Liverpool in 1939 were shipped off to America to work on the Manhattan Project, and the cyclotron came to a standstill, but of course they had cyclotrons in America that we were able to provide them with data, and things came to a standstill really in the UK until after the war, when everything restarted with more of the peacetime academic work was recovered based on the old wartime experiences of building accelerators for other purposes. But I think we really want to talk about synchrotrons more than anything else, because from the Second World War onwards, some major synchrotrons were built in the UK, which were actually not necessarily the biggest in the world, but certainly competitive with other people in the world. There was a whole era went through, and in particular, you can see by the E's here for electrons, as opposed to the P's for protons. There are lots of E's. The UK always had a strong electron accelerator influence, and that, if you like, came really from the users. The particle physicists in this period of time were interested in electron production, and there's very much that rather than proton production. Not entirely, because of course down here at Rutherford Laboratory near Oxford, RAL built a 7 GeV proton synchrotron, but it never, as far as I'm aware, didn't do anything vital. I don't want to belittle the use of an accelerator, because I'm sure a lot of very good important work was done on it, with developing theory and experiment. But if you like, that 7 GeV proton synchrotron was already a small energy. By that time around the rest of the world, much higher energies, 20, 30, 40 higher energies were being produced, even higher in fact in the end. And the one on the bottom of the list I want to talk about here is the NINA 5 GeV electron synchrotron, which was built here at Daresbury. So the origin of Daresbury Laboratory was basically the northern universities, which were very powerful and strong in particle physics at this time, Manchester, Liverpool, particularly even Glasgow, Sheffield. They wanted to have a high energy electron synchrotron in the north of England. And these guys, Cockroft was still around 1960 and 61, and Cockroft really sort of, not pioneered, but he really sort of took over the proposal. And it was very important, his support. If Cockroft hadn't supported this site, it would never have existed, which is one of the reasons why we call this the Cockroft Institute. The other reason is he was born in Bolton, so we sort of needed an important figure who was a northerner, just as a symbol, if you like. Cockroft proposed the Cheshire site. There were a number of sites being proposed. What was the most significant characteristic of these sites, apart from accessibility? It was the stability of the ground. In this period of time, in the 1960s, accelerator builders were obsessed with ground stability. They realized that the machines needed correction. They realized that machines on soggy ground would move around a lot and would have to be continually recorrected because the components weren't stable with time. So they thought, what do? We build it on a stable foundation. What's the best stable foundation you can get in the UK? Sandstone. So there are sandstone outcrops which are close to the surface, on which you could bury the foundations, if you like, of an accelerator. So all of the sites being considered this time, including this one, which, if you know your geology at all, is now on sandstone outcrop here where you're sitting at the moment. The sandstone is down below a lot of muck, but it's only about 50 feet down, 60 feet down, so you can excavate quite easily to that. And so NINA was eventually built, this 5 GeV electron synchrotron, these are small sums of money at the time, at Daresbury, with these universities here. Lancaster University was only opened in 1965, 64, 65, I think the university was built. So it was a brand new university, which is why I put it in brackets, because in this period here, Lancaster didn't exist. But as soon as Lancaster came on the scene as a university, it had a very powerful, important particle physics department from, I don't know, 65, 66, 67 onwards, when Lancaster came into being with postgraduate work. Just a couple of photographs just to amuse you. So here's the site in 1964, looking from up the hill, looking down the hill towards the canal and the River Mersey. And there's a couple of things you can see here is the start of the ring that's going to be built. And a couple of things you can notice. First of all, you can see we have a coal-driven train from the era. You can also see, if you look over the river here, there's no power station. So you can date the picture as being a rather an old picture, but it's just amusing to look at. In that era, when we used to be at the laboratory, because I came here from about 1967 onwards, you could actually see here is Manchester Ship Canal. And in that era, every 20 minutes you'd see a boat, several an hour. Nowadays you never see a boat, but in that era, well, I mean, I know they're still used a little bit, but in that era it was like a motorway with ship traffic. So here's the ring, and here are some concrete pillars being sunk down to this sandstone bedrock. Here are the pillars. You see where the foundation is. This is inside the ring. The laugh about all this is it was a complete load of rubbish. And if you think about it, if you're on a pillar like this, and your pillar is down on the ground, even if the ground at the bottom is only slightly moving, you've got an amplification effect. So the top moves a lot more than the bottom if it sits on these pillars. So in fact, I think it always was a myth. And in fact, no modern accelerator bothers about concrete and sandstone. People, it's just irrelevant nowadays to accelerate. And if you really need to be a stable machine, I mean, you don't want to build it on mud, obviously, but you'll see a machine later on which was built on a riverbed with alluvial stuff at the bottom and everything. So it's not a big deal. You can compensate for it. There may be some cost implication, but it's not a killer blow. That's just a amusing thing for you to see. This canal here was breached during the building. Somehow they tried to get a power cable and they cut into they didn't go deep enough and the water all drained out of the canal for about 5 miles, which is highly embarrassing. Nowadays will be a bad PR exercise, but in those days people didn't have PR. There's Nina. So here are the bending magnets, and here is a radio frequency cavity. It's a pillbox cavity. Actually, there are 3 pillboxes, one after the other, within here, and the accelerating field goes this way. And here's the waveguide. And this machine was running at about 400 megahertz in that era. You'll find lots of machines running at 350, 400, 500 megahertz. Does anybody know the reason for that? Why that frequency is chosen? Well, it's chosen because it's the television transmission frequency. And so accelerators people again took advantage of industry, and from several decades ago realized that the best way of them getting themselves cheap radio frequency equipment was to make sure their frequencies were compatible with major industry standards where stuff was surplus or being produced massively. Or we've gone a bit away from that lately, but that for a long time was the driving force behind these. I mean, this laboratory nowadays is a 500 megahertz, about everything built here was 500 megahertz for about 20, 30 years. These magnets here, you'll also see there are none of those quadrupoles in this machine. These are called combined function magnets, and the poles are not parallel. The poles are sloped alternately with a wedge on them. And the wedge field is like the quadrupole field. It's a gradient field where the field varies with position offset. And so you built in the focusing into the bending field. The bending and focusing fields were combined within a single magnet. And these are F and Ds, because you start out with the F and D idea. So one type of magnet wedge was out and one was in. This is a bit of history. Harold Wilson opening the laboratory. And this is the first director of Daresbury Laboratory, called Alec Merrison. This is 1967, when the lab was in effect opened. I only showed this for fun. Here's Cockroft as an old man. Well, I say old man, he was probably about my age. Not much older anyway. And this is Chadwick. This was Chadwick's 75th birthday in 1966. It's the only picture we've ever had of Chadwick at the laboratory. Chadwick, you'll recall, discovered the neutron. So, the end of particle physics in the UK came around the late 70s. It was a condition for us to join the SPS at CERN. The UK was only allowed to join by our British government if we shut down all our national programme. So the Nimrod accelerator was closed at RAL. The Nina accelerator was closed at the UK. Can you make sure you sign in, if you please, before you... Sorry, you've had a bit of problem with travelling, I guess. So at this period, these 2 machines had to be switched off, and thought began to be given for a replacement. What do we do instead, perhaps nationally? And alternative major facilities were being sought. The nuclear structure facility, if you remember the dates from earlier in the talk, came on at this time in the 1970s. So already there had been some sense that this might happen. So nuclear physics was done at the NSF. So nuclear physics nationally was getting itself a big accelerator in exchange for closing particle physics down within the country. ISIS, which I'll talk about in the second lecture, ISIS was underway in RAL as a neutron source, and the SRS, which I'll now come to, synchronous radiation source, came in place at Daresbury. Right. So let's just say a little bit about radiation from particles, or in particular radiation from electrons. I mean, you all know, or should know something about radiation. If you accelerate a charge, it radiates. It's just a fundamental of nature. In a non-relativistic charge source, you would get this pattern, this field pattern around the electric dipole vector. If, however, you look what happens to a particle which is being accelerated, you get a different picture. And the properties of this were calculated a long time ago, amazingly enough, by Larmor and Leonard Schnott. And they came up with this formula here, which is you need to think about a little bit. This says the power emitted by an electron scales as the fourth power of the energy and the second power of the radius. In other words, the radius is actually linked to the energy as well. So this applies to synchrotron electrons, so it applies, so it's called synchrotron radiation. And this is a very severe problem. This fourth power scaling law is a huge scaling law when you start to think about it. And very rapidly, an electron which is accelerated to hundreds of MeV starts to emit significant amounts of synchrotron radiation. Significant in the sense of perhaps comparable to the amount that you're trying to put into the beam. So even accelerating it becomes difficult. Never mind the stability problems. Just quickly, so of course, if you accelerate from the rest frame into the laboratory frame with an relativistic type acceleration, the emission shape changes into a forward cone. So now the emission of the radiation all goes forward with the part like a searchlight in front of the machine with an opening angle gamma, where gamma is mc squared, the usual expression. So 1 over gamma. So as the energy goes up, the focus of the cone gets narrower and narrower. So in a real accelerator, you get this narrow cone, the electron goes around the bending magnet and it emits radiation through a cone of synchrotron light. First observed in 1947. Now, this was seen as a real menace. I mean, this is rubbish. This is what you don't want. This is wasting the energy you're trying to put into the machine. And so it was seen in a very negative light for many years by accelerator people. However, it turns out that if you start thinking about what's in that cone, what are the properties of that radiation, you can work out roughly the sort of frequency that's in there by thinking, where does it come from? Well, if you're the observer, what is the length of the pulse that you see as an individual electron goes around this orbit? Well, this electron emits, let's say it emits here. So it emits here towards the observer. So that at some point arrives at the observer. And then the electron continues around the curve, around this opening angle of 1 over gamma. And at that point is the end of the emission. So what you want to work out is the difference in path between that length there and the arc. And that gives you the duration over which the radiation is received down the line. And that gives you the pulse length. And if you, I think I had some extra terms come in if I push this button. And you now find that the length of this chord versus the arc difference gives you a typical wavelength given by this formula. And if you put some numbers in, say 2 GeV and 1.2 Tesla for the field strength and the energy of the electron, you come out with 1 angstrom. So you've got an X-ray beam from electrons of this sort of energy. So this is the sort of energy, and these are actually the real parameters of the synchrotron radiation source that was built here, the national source, 2 GeV and 1.2 Tesla for the field, which gives you a bending radius of 5 meters and a gamma of 4,000, and you put them in and you discover you've got yourself synchrotron radiation with an X-ray component. In fact, this is the generalized solution for all such beams. This is not just for the fixed end, this is for all energies, etc. This is now just relevant to a critical frequency which characterizes more or less the peak of the radiation emission. But it has this very flat shape at low energy, and at high energy end it dies very rapidly. So generally people obviously want to work in this region around here if they can, although they get this bonus of the very low energies still have quite a lot of emission, but the high energies are cut off. So this determines your requirements for your machine, and it was what required the 2 GeV. And just very quickly, this broad range source gives you lots of access across the spectrum. It includes infrared right the way through to hard X-rays within the spectrum. What can you do with it? Oh no, I want to just show you that. That's just a bit of fun. Some of you may have seen this picture before. That's the Crab Nebula, which is a beautiful picture. And this stuff here that you can see, which is called synchrotron radiation. So synchrotron radiation is out there in space, particles, electrons being accelerated within fields in interstellar space. And there it is, Crab Nebula, a beautiful picture. Just a little bit of an aside. So the SRS was designed in this period when particle physics was being closed in this country. The SRS design study was completed in about 1974, and in 1980 the SRS was commissioned here at Daresbury and had some upgrades and did some pioneering work and ran in fact till 2008. Now I want to say a word about storage rings, because the synchronous radiation source that was built here was an example of a storage ring. We haven't talked about storage rings yet, we're talking about accelerators. And an accelerator sort of takes the beam at low energy, takes it up to high energy in that synchrotron with that radio frequency system. But what you really want is the beam to be stable and stored at a fixed energy for a reasonable period of time to do experiments with it. So synchrotrons can be turned into a storage mode by ramping to the energy you want. No longer ramping the energy, but just putting enough power into the beam to preserve the power loss from synchrotron radiation. So you've now got a stable energy beam, which hopefully can stay there for quite a long time as a high current. What is that lifetime set by? Well, losses are caused by various processes in that beam. Scattering off the gas. If your vacuum isn't good enough, you get scattering off the gas. Well, inevitably you'll get scattering off the gas. These systems can be hundreds of meters long, so it can't be negligible vacuum pressure. There has to be significant pressure in there. And when you take account of this factor, which is quite a frightening factor, that to stay for a few tens of hours around a ring of say 100 meters typical size, that is the number of turns. Now, the only people who previously studied that number of turns of stability were astronomers who studied stability in gravitational systems, and that's really hard work modelling what happens over 10 to the 12 turns. So you can imagine the various system solutions have to be done. There are basic instabilities within the beam itself. If the beam becomes very high current, there start to be things which I haven't got time to talk about here, but where you can imagine. Let me give you one example. If you have a very high current beam, well, let me go back a stage. If you have a current close to a conducting sheet, you can go to your physics textbook and you can see that the current induces currents within the sheet, eddy currents, if you like. Now this happens in an accelerator. If you have a metal chamber and the beam goes past you, remembering the beam is a current in effect, then that current, particularly remembering it's pulsed and bunched, and therefore has a very high frequency component, can induce currents within the chamber, which could do two things. First of all, they can cause losses within the chamber, actually heating of the chamber in extreme circumstances. The other thing they can do is they can themselves then create fields, which the beam then sees. So, and it can actually see from one bunch to another. So we can get one bunch coming along, inducing currents in a chamber. The next bunch comes behind it and sees the field decaying from what's left behind. And you imagine the possibility that you could have either positive or negative feedback in this circumstance. If you get positive feedback, the beam blows up and gets lost. If you can arrange negative feedback, it's stable. So there are lots of issues here. In addition, in electrons, there's something called radiation damping. Remember that formula, P equals e to the fourth, power goes as e to the fourth. So if your electron is too high in energy, then it will emit a lot more radiation, and it will then come back towards the right energy. It's a bit like that phase of synchronous picture that I didn't really tell you too clearly about. But you can see the process. If the beam is too low energy, it emits less synchronous radiation, and it gets closer in the next turn to the stable energy. So you can see intuitively, you can see there might be something called radiation damage. It doesn't work for protons because there's no radiation emission in protons. And I should have stressed earlier that in the synchronous radiation power emission formula is the mass of the particle. So the proton has such a high mass that in effect it doesn't emit synchronous radiation until it gets to like LHC type energies, huge energies, before you can get significant amounts. So there's a quick picture of the SRS, a LINAC, a booster, 12 MeV to 600 MeV. This booster went at 10 Hertz, so it's a bit like filling a bucket of water by switching a tap on 10 times a second until you got as much charge as you wanted in here. Switch off the injector, ramp to 2 GeV, and turn on the storage beam. And just to show you where it was, here's a picture. Here you can see is the old original Soy Drink. It was in here. And we're here, aren't we? Over here. This is a picture before these buildings were built. There's a picture of a little booster. So now we get this concept that you might well be building several accelerators in a chain to get to high energy. You might want several accelerators, each doing its job over a limited range of energies, and gradually build up to the final energy you want, which in this case was 600 MeV. That's a nice little picture of the original booster here. I don't really want to say much about that. There's an example of the atmosphere that you needed to get stored beam lifetimes of this length. Just wanted to highlight that to you. You really need really good vacuum. There's an example of the decay in a real machine. So you could actually run this machine and fill it once a day. So you could come in at morning at 8 o'clock in the morning, fill it full of beam, switch in the beam storage mode, and leave it right through the day into the night. And the next morning you would fill it up again. Or you might do it twice a day, but typically it was done once a day in the late stages of that machine's lifetime. That's just showing you synchron radiation. Synchron radiation comes out of this pipe. It just comes out, remember, tangentially to the circle with this 1 gamma opening angle. There's an example of real synchron radiation here, ionizing the air. Quite frighteningly intense when you look at it. This is just showing you that the use of synchron is a little bit of an aside really. Synchron radiation beams are a bit like particle beams. They have focusing mirror systems and they have deflection systems and monochromators onto samples. And just to show you quickly the sort of thing that's done, particularly biology, studies of X-rays, crystallography, virus structures. Foot and mouth disease was studied here in the early days. Light harvesting photosynthesis molecules. This is just building little tiny motors, nanoscience that we call now. And this is when the laboratory hit some sort of fame because John Walker shared the 1997 Nobel Prize for Chemistry by experiments used in the FS. This thing here, which I can hardly even say, enzyme, is this molecule rotates, as you can see here in the model of it. And this is what absorbs the energy from sunlight in organic compounds. Really good stuff. Remember that the synchron radiation spectrum depends on the field strength. And if this was not, because the cutoff it goes pretty fast, if you want to get to somewhat higher energies, you want a higher field. And instead of building a whole machine of high fields, you can put an insertion in one straight like this. So here's the normal device. This is one of those double bend achromats. So this is not one magnet. This is symbolic of a double bend acromat that you saw earlier. You've got this straight section. You put this little chicane in. So hopefully you don't notice it much. You may notice it in the machine. You have to be careful about it. But this is a way of inserting it, and this is done here with a superconducting magnet in the SRS. This was done a long time ago, 1980-ish, and it worked very well. Just to show you that all light sources were that big, here's an example of a machine that was built by Oxford Instruments in the 1980s, in a very early example of an attempt to introduce particle accelerators into X-ray lithography for semiconductor manufacture. So IBM bought this machine. You see how small it is? It's got two superconducting dipoles at each end. It's got a couple of quadrupoles in it. And this is on an airbed. And this guy here can actually push this whole accelerator around. This thing was put on a ship, shipped off to the USA, and worked for about 7 or 8 years in the research labs in New York of IBM for lithography trials. Sadly, they decided at that time that they could extend UV lithography for a bit longer from conventional sources. But I see nowadays in the papers all the references to the Americans are thinking again about particle accelerator driven semiconductor production. Well, that's finished now. I just want to point out that these are big accelerators. I'm sure many of you are familiar with this. Here's Geneva Airport, and here's the 27-kilometre ring, the LHC, as it is now. As you'll see later on today, it's not built for the LHC originally. Huge system. I've got 2 more slides before we break. All right. So there's a step back for it and see what we've learned and what we think about. If you're going to work in accelerator physics, what are the generic challenges of accelerator physics? Well, these are the systems that you'll be using. Electrodynamics, it's nearly all classical. There's very little application of quantum mechanics. So if you're a quantum mechanics fiend, it's probably not the right field for you. But if you're not, then it probably is. Single particle dynamics, all these various transport stability, nonlinear dynamics, tracking, differential algebra, all these techniques are used mathematically. Some of you may want to work in a more theoretical area like this. Some of you may want to work in a more practical area. But this is extreme dynamic behavior, weight fields, space charge, coherent instability. These are the things I've talked to you about. Things interacting back on the beam interacting with itself in some cases. All these things cover from production, the transport of beams, the injection into accelerators, extraction, manipulation, delivery. All of this requires major code development. There are big codes now available, and you could say this is a mature field, but there's always room for more new codes and new ideas for modelling new problems. At the end of the day, we've now moved to this era within the last decade or so, the last 5 or 10 years, we're now producing accelerators with particle beams with pulse lengths now sub-picosecond, femtosecond requirements, and similarly cross sections of the beam of nanometers. How do you do diagnostics on a bunch which is a femtosecond duration? Well, not 1 femtosecond, but even 100 femtoseconds, or even a few nanometers in diameter. How do you do that? How do you know what the beam is? Well, I just thought I'd just for fun just show you a couple of slides just to finish off this morning's session. And here is the solution to ultra short pulse diagnostics, or one of them. What you can do is you can do some mixings here where you take this electron beam, which is pulsed, which has a very short duration, let's say a picosecond or less, and you send this beam past electro-optic material, which is simultaneously irradiated with a probe laser. And as these two coincide, and this thing goes through here with the electron beam in coincidence, this electron beam imprints the laser. So the pulse here is the real pulse of the electrons, taking a hold out of the laser by the electro-optic interaction. And you can reproduce this and reconstruct it, and this has actually been done to about 100 femtosecond resolution so far. It's quite difficult to get beyond this. And here is a real beam, which is only 100-200 femtoseconds wide, being measured in DAISY in Germany on Flash FEL by some collaborators here, which include, I think, some people from Dundee and Aztec here at Daresbury. And what about the nanometers? Well, how do you do that? Well, you do it with what's called a laser wire. Now, there are real wire interaction machines. Historically, with a big iron beam, quite a wide wire beam, you could push a wire through it and check the scattering as you went through and reproduce the distribution by looking at the scattering. Because if you do that with these beams, first of all, they're very intense, they'll probably melt the wire because the density is so great now and the beam is so small, it has to be nanometers. And secondly, of course, you haven't got the distribution ability to feasible even to discriminate at that level. So what you do, instead of a wire, you use a laser beam. So now they fire a laser beam through the electron bunch and scatter off the laser beam. The laser beam can be made very small and focused, and use a 2D scanning system, and here are some of the results of some measurements. Not quite a nanometer, but certainly hundreds of nanometers. I mean, when I say nanometer, I don't mean 1 nanometer, I mean in the sub-millimeter region, sub-micron region, I should say. So all these systems have been done by people here at Cockroft, and have taken the lead in some of these things internationally. And I'll just finish off by one last slide about the future. There's been a lot of talk in recent years about the limitation on present types of accelerator using radio frequency accelerator structures. Can we ever go bigger than the LHC, for example? Is it realistic to go bigger? Well, I'll say something about that later on. But plasma wake fields has been investigated within Cockroft. A lot of people have been working on this in the UK, at Strathclyde in particular, at Imperial College and at RAL so far. And there's plans to do some work here at Daresbury with the Cockroft as well. The Cockroft people have been involved in some of this work already in collaboration. And there are sort of nature papers on this. And of course, you can get huge accelerating gradients in principle. The maximum accelerating gradient you'll get from radio frequency systems is about 3 orders of magnitude less than this. Even 100 MeV per meter is almost unheard of. A few tens of MeV per meter is more typical of a present system, which makes for these huge accelerators that you'll see after my next talk, in my next talk. But the problem, of course, is you're doing a relative